Welcome to the Foundations of Data Science virtual seminar series. Today we're very excited to have Eric Tchetgen tell us about an introduction to Proximal Causal Inference. So Eric is a professor at the University of Pennsylvania in the Wharton School, as the Ludwig Family's President's Distinguished Professor and Professor of Statistics. Eric got his PhD in biostatistics at Harvard University in 2006, and after that joined as a Professor of Biostatistics and Epidemiologic Methods at Harvard before his current position. And we're very excited to hear today about causal inference and some of his recent work. Thanks a lot, Eric.
Thank you, Clément, for, can you hear me?
Yes.
Yes, okay. Thank you, Clément, for that introduction, and thank you for the opportunity to present my work here today. This is work I've been doing, I've been most excited about, and I've been doing for the past few years. And this is just a brief outline of the talk. I'll give some preliminary remarks to sort of frame the problem. Then I'll describe what's sort of the state of the art in causal inference, which relies on this assumption of exchangeability in order to claim identification of causal effects. And then I would describe our proposal, which we term proximal identification of causal effects, which tries to make a different identification assumption that we believe investigators can more easily and more realistically reason about, rather than assuming exchangeability. Then I'll go over some simulations and application, both synthetic data and real data, and close with some remarks. So this is work of a large group of co-investigators, including former students, postdocs, and some faculty colleagues over the years. And I'll go over a short list of the progress we've made over the past few years towards the end of my talk. But today I'm really going to talk about just cover sort of the framework and give a brief introduction to this topic. But we have in our group, as well as with other groups, have also contributed a number of different directions in which it's been shown that proximal causal inference actually shows promise for identification across different challenging problems of querying about causation. Now, so as by way of background, a standard assumption for causal inference from observational data, where one is aiming to identify the causal effect of a potential intervention on an outcome of interest, one typically relies on an assumption that one has measured a sufficiently rich set of covariates to ensure that one can adjust for confounding, that within covariate strata prior to the intervention, the individuals who receive the intervention are comparable, exchangeable with the individuals who do not receive the intervention. And so we get a fair comparison. We can isolate the difference in the outcomes between those two groups within levels of the covariates as being a causal effect. As you can imagine, there's quite a bit of skepticism about this exchangeability assumption in observational studies, and that's because it's often the case that in these situations, one does not really have control over the assignment mechanism, and so this assumption is not a testable assumption by itself, and it hinges heavily on an investigator's ability to accurately measure covariates, capturing all potential sources of confounding. And this is, to be clear, this is true even in the most well-designed studies where there's a good understanding of the assignment mechanism, but unfortunately there still is a measurement issue as to having measured the right covariates on the right scales with appropriate accuracy. In those situations, claiming that on the basis of observed covariates, you've attained exchangeability is often challenged. Realistically, confounding mechanisms can rarely, if ever, be learned with certainty from measured covariates. And so if we're really being honest with ourselves, in practice, the most one can hope for is that covariate measurements are at best proxies of the true underlying confounding mechanism operating in a given observational study. And so in a very well thought out observational study, very well designed observational study where one thinks about the mechanisms that might lead to confounding bias, the ability to measure the source of confounding is limited in general. And once we make that, and we acknowledge this limitation, okay, whether because we haven't thought about all the source of confounding or because we don't really have an ability to measure the actual source of confounding, even if we know what it is and we have some probes of it. Once we acknowledge this obviously invalidates any causal claim made on the basis of exchangeability conditional on the covariates that you in fact measured. And so in today's talk, I would like to introduce a framework for proximal causal learning, which while explicitly acknowledging that covariate measurements are really imperfect proxies of confounding mechanisms, still enables one to potentially learn about causal effects in settings where exchangeability does not strictly hold on the basis of your measured covariate. And so just to jump right into it, here's a little bit of formalization I'm going to use in the talk, where I'm going to be operating in an IID setting, and I'll discuss later on non-IID settings where we've extended this work. So we have an exposure A, it's a treatment of interest. We have an outcome Y, and then we have a set of measured covariates L. And we'll use the potential outcome framework for reasoning about causation. Let Y little a denote the potential outcome had possibly contrary to fact a person received treatment A. And so this is the outcome we wish to learn if we were to possibly contrary to fact intervene and set the treatment to a value little a. We aim to identify population average causal effect corresponding to a contrast of counterfactual averages beta A. So we want to learn this function of little a for different values of A. And so there's a population average causal effect or the average treatment effect. Now, what are the standard formalism for identification? Speaking of identification, the challenge here is, of course, in a data set, you don't observe Y little a for all values of A. If you're fortunate, you observe Y little a for the value of little a that the person actually took. And so the idea of causal inference is to think hypothetically what would have happened to that person if they are taking a value of A that maybe conflict with the one that he took. And you look at that contrast, and we call that a causal contrast. And so if you want to think about this, Y little a is sort of a latent variable. The set of Y little a for all values of A, we presume here, the leap of faith is we presume that they exist for each person, and that's how that kind of gives us a mathematical definition of what we're referring to as a causal effect. Then we want to learn about this latent variable Y little a. We have access to a single measurement of Y little a, which is the Y, the outcome observed for the treatment value actually taken. And unfortunately, we worry that the value of A the value of Y that's revealed is connected with a person's health status. If you're in the healthcare sector, it's features of the underlying person that may have been used to decide which value of Y would be revealed, and that's the concern about confounding. And so, what are the standard assumptions for identification of this beta A functional? It's typically assumed that your observed outcome matches the potential outcome Y for the value of A that you actually took. That's so-called consistency assumption. We also typically make a positivity assumption that for any realized value of the covariates, there's at least one individual who takes the value little a that we're interested in. And the most controversial assumption of all is the no unmeasured or confounding or exchangeability assumption. On the basis of measured covariates, which essentially says that the potential outcome we care about would become independent of the treatment value actually received, condition on L. And this is an important point because the treatment value that you did receive drives the outcome that we actually do observe. And in order to recover the potential outcome we care about, we need that selection process of revealing the potential outcomes to be independent of the actual potential outcome. Okay, so this is usually a formalization of how to think about non-measured confounding. If you will, you think of the potential outcome as the ultimate source of confounding, and conditional on your measured covariates, you render the potential outcome as not being a predictor of your treatment. So there are various ways of conceptualizing this. Another way of conceptualizing this is that across treatment values, conditional A, L, the potential outcomes are balanced. So this is a sense in which we talk about, this is referring to exchangeability. It means that conditional on the covariates, the individuals who received the treatment and the individual happen to have received the control are comparable in terms of their potential outcome for any given value of little a. Okay. Now, very important to note that this is not assuming that y is independent of a given L, which would be a causal null assumption. Okay. This is an assumption. This assumption is not testable, whereas y independent of a given L is a statistical assumption. It's a statistical hypothesis that is empirically testable.
So I have a question about the goal. So here, little a, do you want to learn that functional beta for all little a's, or for like some specific sets that you specify ahead of time? Like, what is the
Yeah, that is a good question. All of the above. It's typically the case that if A is binary treatment, you want to contrast the potential outcome if I treated everyone in the population to the potential outcome if I treated no one in the population. And so that would be comparing beta for A equals 1 to beta for A equals 0, taking the mean difference in that potential outcome, and we call that the average treatment effect. In some cases, such as, for instance, the example of smoking, you might say, what is the cancer rate in my current population? So that's the average Y, the observed average Y. And then you might ask, what would be the cancer rate if I were to prevent everyone from smoking, right? And so in that case, you're only interested in Y0, okay? In that case, it doesn't make sense to think about what is the cancer rate if I forced everyone to smoke. That is not a public health message we want to put out there. And so all of the above, I'm going to focus for the purpose of this talk on a given value little a that you hand to me. And we'll do everything generically for that. And then that once we have that for that value of a, as the value of a is generic, you can make it whatever you want. And the point is you then can create contrast across values of a. Okay, so that's a very good question. Yep. All right, so let's talk a little bit about this assumption of exchangeability that's under attack in this talk. Okay, and I want to use directed acyclic graph to demonstrate scenarios under which it would hold. So the first one, I'm going to call these variables L proxies of type A. And these variables L, in this case, would satisfy this condition 3 in the sense that they block all backdoor paths, all non-causal pathways from the treatment to the outcome. So we care about this association here. That's the causal association. And the association that goes through L is completely non-causal. All right, and so the idea is if I have adjusted for all common causes of A and Y, I would have adjusted for L, for confounding. So this is a situation where we assume we've measured all common causes of L, of A and Y, L, and I'll refer to these common causes as proxies of type A. All right, and so under this first scenario, assumption 3 would hold. So this is a hypothetical example where assumption 3 would be reasonable. In scenario B here, we have an unmeasured common cause, U. So U causes A through L and causes Y. And U stands for unmeasured common cause. These could be vectors, it can be anything, okay? And the idea here is that L, in this case, is what you have observed. And L, in this case, is going to be said to be a proxy of type B. If it's all causes of A that share an unmeasured common cause with Y. And so in this case, in fact, you can still claim that assumption 3 holds because L will intercept all pathways from the unmeasured confounder to the treatment. Okay, so this is again will be a reasonable setting in which exchangeability would hold. And then we have the mirror image of that setting, where L now are all causes of Y that share an unmeasured common cause with A. And we'll refer to such an L as a proxy of type C. Now, usually, if one is usually willing to make this assumption, we don't necessarily ask them to spell out the causal graph. Usually, in a given application, we might make the assumption and go our merry way to estimate the quantity of interest conditional on this assumption holding. Now, the main reason I'm going through this exercise is to motivate proxies. There are different types of proxies. All right, so the last case I want to demonstrate here is one that basically overlays these three situations, where now Z is, let me start with X. X is a proxy of type A. Okay, Z is a proxy of type B, so all causes of A that share on unmeasured common cause with Y. And U1 and U2 are unmeasured common causes. And W is a proxy of type C, all causes of Y that share an unmeasured common cause with A. And so in this situation, the vectors Z, X, and W, they are observed, would in fact constitute L and would suffice to adjust for confounding. And so in this situation, we would again say exchangeability holds, conditional on L, which is X, Z, and W. All right. Under these three assumptions that I just stated, consistency, positivity, and exchangeability, one can show that the average causal effect, beta A, this functional for any value of little a, is obtained by the simple functional of the observed sample. All right, so you regress your Y on A and L, get the mean conditional value of A you care about, and conditional on L as well, over all values of L, and then you simply average over the values of L with respect to the distribution of L in the entire population. It's very, and the reason this is a special formula is because this is not a marginal mean of Y given A, by virtue of us not conditional on A in the density of L. This is the simplest instance of a formula most commonly known in the field of biostatistics and epidemiology as the G formula. It has different names, the truncation formula, the interventional formula. Depending on your background, you might have seen this formula under a different name. I'm going to use the G formula associated with the work of Jamie Robbins, because in fact, the G formula will generalizes to settings where you might be interested in all kinds of generalized treatment regime, dynamic regimes, and so on, time-varying settings, mediation analysis, all of those settings. And we've demonstrated that the proximal inference framework will generalize to those settings as well. And so just like we have a G formula here, we'll derive a proximal G formula, which will be a generalization of this identifying formula for cases where you allow for unmeasured confounding, provided you have certain access to certain types of proxies of the unmeasured confounder. All right, so now let's get to the main reason we're here today, talk about unmeasured confounding. And so I'm going to focus on these two figures where now I've clearly announced that I do admit that I do have unmeasured common causes of A and Y, that X, Z, and W do not suffice to adjust for. Okay, and so in these figures, these are settings in which exchangeability fails, despite having measured covariates L, which includes X, Z, and W, depicted in these graphs. And this is owing to the presence of U, the unmeasured common cause of A and Y. You have untractable confounding, and you would get some hidden bias in any analysis that does not have access to U. Any standard analysis that does not have access to U. And so what's important about these graphs is if I can collect proxies Z of type A, and proxies proxies Z of type B, and proxies W of type C, and we'll refer to them as treatment proxies. So these are Z. These are common causes of A that share an unmeasured common cause with Y, and W causes of Y that share an unmeasured common cause with A. Okay. Then we will show that in these situations, it is possible to identify the causal effect, even though we haven't measured for U. And note that this, in many cases, the graph that actually holds will be this one, where in fact, all you need is Z and W are proxies of U, of the unmeasured common cause. They need not be causes of A or causes of Y, respectively, like I had them displayed here. The important part is that they are relevant to the source of confounding. What do we then call valid treatment and outcome confounding proxies? They have to satisfy these two conditions that are encoded in these graphs. And this is essentially, it's very intuitive. The first one essentially states that if I had measured the source of confounding U, and my proxies of type A, conditional on the treatment, then Z would not predict Y. And so this is this notion of Z being a proxy in the sense that if I actually measured U, I wouldn't need to measure Z. Z is no longer a source of control for confounding. It's informative about U. And so typical to, this might, those of you familiar with measurement error problems, this is a very similar notion to measurement error problems, that if I correctly measured my variable of interest, the mismeasured variable will no longer be relevant to the system. And so in this particular case, treatment proxies become irrelevant in a very specific form, equation 5, that they are no longer predictive of the outcome, because the only reason they were predictive of the outcome is that they are correlated with U. If I adjust for U, they're no longer relevant. I can throw them away. Okay, so that's Z will be, that satisfy this equation, treatment proxies, provided they also satisfy the following equation. And this is the notion in which W is in fact a valid outcome confounding proxy. And so likewise, in sort of a symmetry statement to 5, conditional on U and X, W now is no longer relevant for the vector of treatment, the treatment and the treatment proxy. And likewise, it will not be useful for adjusting for confounding, right? The notion that confounders are typically associated with both the treatment and the outcome. And so Z and W are not real confounders. They're proxies of the source of confounding. And so once we have access to the true source of confounding, they become irrelevant. All right, let me pause there for a second to see if there are any questions. This is an important part because this is what we're going to define as, these are the definition of what we'll call valid proxies. And I'm going to go through some examples next. All right, so examples of proxies of type B and C abound in observational studies. I'm actually going to argue that most covariates and features that we observe in observational samples, because the observational samples are often of convenience or are constrained by study budgets, most of the covariates in well-designed studies are actually proxies. And so the task is to figure out what kind of proxies are they. In observational studies, evaluating the effects of a treatment, I do a lot of work in public health. And so I look very much concerned with evaluation of all kinds of treatment on outcomes using observational data. So for instance, evaluating such an effect, there's a general concern that patients either self-select according to health-seeking behavior or are selected by their physician to take the treatment based on prognostic factors for the outcome. And so if you're aware of this, then as an investigator, a diligent investigator, you would endeavor to record lab measurements and other clinically relevant covariates data available to the physician and the patient at the time when they're considering taking the treatment. How do we do this in research? Well, we put out questionnaires that the patients fill out. We look at electronic health records. There are all kinds of ways of accessing that information, or we measure biomarkers in a lab, all of which give a measurement error prone snapshot of the underlying physiological mechanism or disease status at the source of confounding bias. And so for instance, to further make this concrete, in HIV studies, before universal test and treat, which means that nowadays they test a person for HIV if they're feeling a little sick. Once they test positive, they immediately put them on treatment. Less than 5 years ago, it used to be the case that what they would do is they will monitor a patient after they test positive. And once they get sufficiently sick that they require treatment, they'll put them on treatment. And there were many reasons for that. First, there was a limitation in the number of treatments available. And we're concerned about non-compliance. We're concerned about toxicity of the drugs. They're very highly potent drugs. The main driver of when to treat an HIV patient is a CD4 count, which is a measure of immune system. How well is your immune system doing in fighting off infections? And so it used to be the case that to study anything about HIV, you will measure CD4 count. You would also measure the viral load in the blood of the patient, okay, in HIV research. So these are important biomarkers on the immune status and the disease progression status of the patient. Now, these variables are measured in a lab. They're measured with error. They're a snapshot at one point in time. And so they don't present a whole complete picture on the immune system and the disease progression of the patient. They are highly associated with them. They're highly informative, but they do not control for the source of confounding. Source of confounding here is how sick is the patient, how much is their immune system depleted. So in that sense, CD4 and viral load are proxies of the source of confounding. ICD-9 codes to measure comorbidities in comparative effectiveness studies, food frequency questionnaire and nutrition studies, cognitive function screening tools such as the MMSE in cognitive research, customer characteristic in business analytics, seller characteristics as well in those settings. All of these variables are typically variables that features that people worry about adjusting for. And the point I want to make here is that all of these variables are actually proxies of the source of confounding. There's a good reason to want to measure them, but we should acknowledge that, and that's the best we can do. Is we think carefully about what a potential source of confounding, we try to measure them, but then we often rely on the assumption that we've done a perfect job in measuring them. And the point is that even in the most well-designed studies, that is not the case. There will be some degree of measurement error. There will be some degree of unmeasured confounding. And so the proposal here is for those studies, for those cases where you have done a good job and you have measured a number of proxies of the source of confounding. If you haven't measured a source of proxies, good proxies for unmeasured confounding, all bets are off. There's no magic here. All right, so I'm going to go through a simple example to give you an intuition of, now that we have this definition of these two valid proxies, how do we use them to adjust for confounding? But like all good examples, they assume that they start on the premise that the world is linear. Okay, linear models is all you need to understand causal inference and statistics. Anything beyond that is just a cherry on the pie. Okay, a cherry on the cake. So in order to ground ideas, we briefly describe the proposal, assuming the following simple system of structural linear models compatible with our DAG. So the model is a model for the outcome, conditional A, Z, X, and U. So that's the outcome, conditional A, Z, X, and U. And as you can see here, the left-hand side, and so it's a linear model in those variables, and the left-hand side does depend on Z, but the right-hand side does not, and that's including the fact that if I condition on U, Z becomes, Z is a treatment proxy, it's no longer predictive of the outcome. And so it falls out. And of course, with condition on U, this is a model of interest. It's linear, that's not realistic in most settings, but it will suffice to ground ideas. And so we care about identifying beta A, which is the causal effect of interest. One union change in intervening on A, what is the corresponding change in Y? Conditional on U and X. We also specify a linear model for W, conditional on A, Z, X, and U. And as W is a valid outcome proxy satisfying this DAG, the left-hand side conditional on them, on Z and A, however, the right-hand side does not. That was part of our definition of valid proxy. Outcome proxies W is that neither A nor Z are predictive of W conditional on U. All right. Now, just to walk through what the logic is here, I can integrate over U, given A, Z, and X, for both of these equations on the left-hand side, and I do the same on the right-hand side. These are linear model. So if I integrate over U, I'm taking the expectation with respect to U, given A, Z, and X. And so the mean of Y given A, Z, and X will be a linear model with beta 0. I'm conditional on A, so beta AA. And I'll have here beta U, and I'm replacing U with the mean of U given A, Z, and X. And then this is just beta XX. Okay. I can do the same thing here. I integrate over U given A, Z, and X. And so I again get a linear model in the mean of U given A, Z, and X. Both models, I have two equations that only now depend on the observed data on the left-hand side, because it's the mean of Y given A, Z, and X. And so two equations with one unknown. What's the unknown? The mean of U given A, Z, and X. I can solve the second equation for the mean of U given A, Z, and X in terms of the mean of W given A, Z, and X. And then I can substitute in the first equation, and lo and behold, I get this equation, that the mean of Y given A, Z, and X is a linear model. It's linear in A, It's linear in the mean of W given A, Z, and X, and it's linear in X. And the most important part of this is that the coefficient that goes with A here is the original coefficient I cared about. And so it suffices to fit this model in two stages. I first regress W on A, Z, and X. That is, I regress the outcome proxy on the treatment proxy, the treatment and covariate. And I use that in a model for the outcome. And this now becomes an adjustment for confounding. It uses W and Z as proxies of U to construct this control variable. All right, and so this suggests the following simple approach. If the world is linear, you fit an initial model, you regress W on A, Z, and X, you get the predicted values, let's call them W hat for each individual as a function of their A, Z, and X. And then you fit a linear regression using alternate least squares of Y on A, W hat, and X. It's very important to note that there's an assumption that I'm making in here. As you can see here, for instance, imagine that Z were not an actual valid proxy for U. If Z were not a valid proxy for U, then this equation would become highly collinear with A and X here, and I would lose identification. Likewise, if W is not relevant with U, this coefficient would be the equation will likewise not be identified. And so I'm really using the fact here that W and Z need to be correlated with U. They need to be relevant to the source of confounding.
So
yes, go ahead.
Sorry, I've got a small question about this. So assuming I found, so here there were only two proxies. If I find more, can I just do that with a bunch of them? Do I lose something if I add that? I mean, assuming like gathering more data, but also the errors propagate. Is there like a soft spot about what I might want to do?
So the general answer is you can use multiple W's and Z's. And when I get to the non-parametric, I'll say more about this when I get what the restriction is when I get to the non-parametric setup. But the answer is yes, you can do this with multivariate W and Z, but there is still the same caveat. The more informative they are, the better. Okay, and so there's a trade-off between checking for sort of like in an IV analysis. You might have many IVs and one exposure, and you always want to check that first state regression of the exposure on the IVs to make sure that they are relevant. Because otherwise, you're just adding noise, and it could actually amplify your bias. And so in this case, you want to make sure that the Z's are actually predictive of the W's, given A and X.
Thanks.
As adjusting for W hat, the bias is the least squares estimator of beta A, conditional X. We refer to W hat as a proximal confounding control variable. The system of linear structure equations considered above is overly restrictive. It assumes linearity, there are no interaction. And so my goal now is to explain how do we do this non-parametrically. Okay. All right, so I'm going to have two assumptions I'm going to cover to explain how we do this without assuming the world is linear, by allowing non-parametric values. The first assumption is that the following integral equation, and sums can be integrals here, admits a solution. So the left-hand side is something that looks like the left-hand side of my linear model, the mean of Y given A, Z, and X. And I want to find a function of A, X, and W such that when I integrate that function with respect to the density of W given A, Z, and X, I recover the conditional mean on the left-hand side. Now, this is not a trivial equation. It's not always a solution. But if there's not a solution, you'll find out. Your computer will crash and tell you, I can't find such an H. Because it only depends on the observed data. In fact, this is a Fredholm integral equation of the first kind, and there are mathematical conditions for existence of such a solution. So it's very well studied in functional analysis, very well characterized by mathematicians. So we're going to assume first that there is such a solution. Speak a little bit about conditions under which such a solution might exist. But we know when there exists a solution, we're not going to need it to be unique. We just need to find one such H. The second assumption is one that's not testable, unlike the first assumption. The second assumption assumed, essentially, this is an assumption about the relevance of your proxies, that for any function V of U, and could also depend on A, Z, and X, if the mean of that function given A, Z, and X is 0, This would happen if and only if the function itself is 0. And I'll come back to this in a few slides to give you some intuition of what these conditions mean. So these are mathematical high-level conditions. One condition is testable, the other one is not. And we'll come back to them. But suppose those two conditions hold, and we have valid proxies Z and W. Then it turns out that we get an identifying formula. This is what we'll refer to as the proximal G formula, which takes the solution that we have from equation 1, the first assumption, and marginalizes over W and X. And we've shown that that actually recovers your potential outcome mean. Furthermore, we can show that the solution to this integral equation in the observed world under our conditions satisfies a similar equation if you had actually measured U, the unmeasured confounder. And so this is an equation that you can never run. And the point is that any solution to this equation, by leveraging this assumption, second assumption, will also be a solution to this equation. And you can sort of see what then happens. If you recall, the G formula said condition on U and X, and then marginalize over U and X. And so that's essentially what we're doing here. We're using this expression. When we marginalize over U and X, we recover this expression. So this equation is actually an important step in establishing the identifying formula. And so we refer to this identifying formula as a proximal G formula, as I said. And we will refer to H as an outcome confounding bridge function. So this is a bridge function that's related to the outcome variable, right? It's solving. And so as such, it links this integral equation in the observed world to the integral equation in the latent world. And as such, we refer to it as a bridge function. Okay, and we also refer to it as an outcome confounding bridge function. Okay, we also have, I'm not going to have time to get into it, but we have an analog of this for a treatment confounding bridge function, which connects the propensity score to a treatment confounding bridge function. Okay. And finally, we'll have an identified formula that's W robust. If you're familiar with the literature on double robustness, we have a complete analog in this framework of double robustness. I'm not going to have time to get into that. All right, so as I said, the integral equation of our first assumption is known as a Freedom equation of the first kind. And there are conditions in the literature as to when a solution exists, as well as when it's unique. And we discussed this in our paper back in 2018. The second condition is actually, for those statisticians in the crowd, will recognize this as what's known as a completeness condition. And so complete sufficient statistics is sort of part of the foundations of getting a PhD in statistics. Your first course of inference, you'll learn about these notions. And this notion can accommodate both categorical and continuous confounders. And completeness here is really a technical condition which says that for any source of variation in U, there's a corresponding source of variation in Z. And so this is formalizing this idea that Z must be associated with U, must be relevant for U. So in the CD4 count example, it must be that if your immune system depletes, which you have a shadow of that depletion in your CD4 count. Your CD4 count should reflect that grossly. It should go down as well. All right. It's not a one-to-one correspondence. It's just that it needs to be informative. So that's an important point of the proxy relevance. This condition of completeness is actually easiest understood in the case of categorical variables, and it goes as follows. If you have categorical U, Z, and W, with corresponding number of categories DU, DZ, and DW, respectively, in this case, completeness requires that Z and W must at least have as many levels as U, and that completely makes sense. There is no magic here. If I have an unmeasured confounder that has 10 levels, it must be that Z and W, for them to be good proxies, they must have at least 10 levels. Otherwise, I can always find a manifold of those 10 levels for which Z and W do not have any information. And so if I have a binary Z and a binary W, but it turns out my U has 10 levels, I will not get identification. Completeness will not hold, it will fail. Okay, and so this is going back to the question I was asked earlier. So intuitively, Accounting for measure confounding in the categorical case requires that the number of categories of U is no larger than that of either proxies Z and W. This condition provides a rationale for measuring a rich set of baseline characteristics in observational studies as a potential strategy to mitigate on measure confounding via the proximal approach. And so, in fact, it's desirable to measure multiple Z's and W's. The more Z's and W's you have, the more measure confounding you can potentially account for. The higher the requirements of relevance.
Eric, there is a question in the chat asking whether assumption 2 is tight, meaning as in we do not have the condition, is it not possible to identify?
Yeah, so that is a good question. No, it's not tight, it's sufficient. There are settings. For instance, I do a little bit of work in synthetic controls, and synthetic controls have a very natural, it's a very natural setting whereby you can actually, the starting assumption is that this equation holds in the latent world. And so if this equation holds in the latent world, you will not require assumption 2. You will require a different completeness assumption, which is a testable completeness assumption, in which case you will again get identification. And so this, from my point of view, is that these are justifications for the approach, and there are many such justifications now in the literature. And you only need one of them to hold to be able to use the method. They all point to the same approach in terms of the observed data. But these are not if and only if conditions. They're sufficient conditions. It's a really good question. Okay. Hopefully that answers your question. All right, so now let's talk about computation. Unfortunately, unlike the G formula, if you recall the G formula, you run one regression of the mean of Y given A and covariates, and then you integrate over the covariates. And so it's all available in closed form. You specify your models, you can use machine learning to model the means you need and do all that stuff. Unfortunately, the proximal G formula is not available in closed form because H is rarely available in closed form. Okay. The integral equation, such Fredholm integral equation are well known to be ill-posed, inverse problems, and generally computationally intensive and unstable. And so we need some form of regularization. Now, what's important to note is that this is actually not a problem per se relative to our current approach. Our current approach, assuming exchangeability, is an extreme form of regularization. Exchangeability turns out to be a special case of proximal inference. And so it turns out that it guarantees the solution is unique and that H is a conditional mean by assuming exchangeability. And so what we want to do is we still want to characterize when can we get a solution without necessarily going all the way to assuming exchangeability. So this regularization is always part of the game. It's just we want to be a little more flexible in that how extreme we make the regularization. Okay, I'm running a little out of time, so let me speed up a little bit. So now I'm going to describe a simple statistical approach known as proximal G computation, which sidesteps this difficulty by regularizing the inverse problem. And so, very briefly, I think if there are machine learning folks in the crowd, they will probably recognize what we're going to do. So what we've done here is we've taken our integral equation. So if I were to integrate over conditional AZ and X, this would turn into the mean of Y given AZ and X, and this would be the mean of our bridge function given AZ and X. And so this is basically, I've moved the right-hand side of the integral equation to the left, and I've pulled out the expectation. Okay, and the point is that the true bridge function should satisfy this equation has mean 0 for any function of AZ and X multiplied here, because this equation has mean 0 conditional AZ and X. And so what I'm going to do is I'm going to take a set of function, a test set, and a solution set. I can make it a Hilbert space set. I can make these functional spaces. We're going to use reproducing kernel Hilbert space in our application. And what I'm going to do is I'm going to turn this solving the integral equation into an adversarial learning process. So I'm going to say, I want to find H star in a functional space H, such that when I maximize the expected value with respect to the test functions, as this should have mean 0 for any such test function, I find that H star that minimizes the maximum. So I turn it into a saddle point problem. Okay, and we also require a penalty to regularize T. Okay, and so the regularization comes from your choice of sets H and T, the sets for which you want this minimax formulation of the problem to be satisfied. All right, the original integral equation will make the penalty 0 and makes these sets essentially all functions measurable functions. So we're going to reduce that set to a particular class, and we're going to study the statistical properties of those estimators. And so one can view H and T as functional spaces that are sufficiently small in order to regularize the inverse problem defining H. So this has a little bit of the flavor of Tikhonov regularization, but it's not. This is a minimax formulation of an integral equation. These spaces can either be finite dimensional, and I will do you an example with a linear space, or they can be infinite dimensional. Okay. And so we have a paper where we've done this using with RKHS, and Amir Ghazami, postdoctoral fellow working with myself and Ila Schwitzer at Hopkins, is going to be presenting this paper at AISTAT. To illustrate a simple version of the approach, consider the special case where H is taken to be a linear model. Okay, so if I take H to be a linear model, then one can show that the minimax problem actually provides the solution to that minimax problem is exactly the two-stage solution that I presented early on when I assumed the world was linear. And so it turns out that the confounding bridge function formalization of this, which never refers to U, right, doesn't need to assume the world is linear, simply assumes H is linear, gives you the same solution. And so this is another way of interpreting that solution that I described earlier on. All right, so let me just skip ahead a little bit. Just in the interest of time, I'm going to skip ahead a little bit. These are just simulations. I did mention that we have the proximal outcome regression. We also do have proximal inverse probability weighting, and we have a W-robust version that combines the two. And the W-robust tends to perform much better than the other two. And I think this was using RKHS estimation. And so you can sort of see that they are non-parametric models, but the bias is much smaller for the W-robust estimator than for the other two. So I have about 10 minutes. So let me go over a quick example. I could maybe pause if there are any questions. I went over that kind of quickly. And if not, I'll just keep going. All right. So we're going to consider an analysis of the support study with the aim of evaluating the causal effect of right heart catheterization during the initial care of critically ill patients who were admitted to an ICU. And we're looking at survival time up to 30 days. And so this was based on a study that was published back in '92, an observational study. It was the first observational study of this procedure. The RH says the procedure was performed over a little more than 2,100 patients within initial 24 hours of ICU stay. And a little over 3,500 patients were managed without this intervention. The study collected, is an observational study, and so they were concerned about selection into the treatment arm. And so they collected 73 covariates, and I'm listing some of them here. Some of them are socio-demographic variables, others are physiological and other kinds of biological measurements. And the outcome is 30-day survival. There were, we focused on 10 variables measuring the patient's overall physiological status, which were measured from a blood test. And so we're captured really the state of the patient, and we're thinking of them as good proxies of the patient's status. And we focus primarily on 4 of them as our choice for proxies. And then we permuted their choices just to, and I'll say something about that in a few slides. All right, so we fit 2 methods. We fit the simple model where our solution space was a linear model, and so that goes back to that two-stage regression approach. And we also did this. We also used the minimax approach using RKHS. All right. This is just a simple R-call. If you wanted to use the simple linear model, you could just use IV-reg in R. And this is just a call that would specify your outcome treatment covariate you want to adjust for, your outcome proxy, and the treatment proxy. And so using linear models, we've implemented 4 methods. The two I focused on actually, this is the W-robust, kind of the state of the art under exchangeability. In this case, I think we use double device machine learning, which requires exchangeability. And then we use the outcome, the proximal confounding bridge approach, outcome confounding bridge approach, and then the analog that I did not cover today, the treatment confounding bridge approach and the W-robust. And the nice thing about this is you want to see these 3 essentially agreeing as they make they have different modeling requirements, and the most robust by far is the W-robust one. And compared to the approach that requires exchangeability, the effect, the harmful effect of this procedure in this particular population was significantly higher than was previously published. And so presumably this would be attributing that change to the presence of a measure confounding. Obviously, we cannot assume that we've adjusted for all potential sources of confounding. We can only assume that we've adjusted for all potential sources of confounding for which W and Z are valid proxies. And so we did one analysis using parametric models, the linear model that I had earlier, and then one using RKHS, and they essentially agreed. So I'm not going to spend much time on that. So in the 2 minutes remaining, I want to leave some time for question or discussions. I wanted to maybe say something about extensions of this work. So proximal causal inference is really a generic framework for causal inference, in the sense that we've been able to demonstrate that the same conceptual framework can be used for causal mediation analysis, IV analysis with invalid IVs, using synthetic controls to address situations where you only have a single unit that's treated, and interference settings. So this is a setting where we do not have IVs data, we have network data, and we worry about homophily bias. And so we have papers on how to deal with that. Survival analysis, where you have a censored survival outcome. Settings where you have time-varying covariates and time-varying confounding. And then also graphical identification. We have a sound identification algorithm, giving a set of data, figuring out whether proximal inference will provide the right answer. We've also looked at settings such as that are not about adjusting for measure confounding, but rather fixing up a hidden bias. So for instance, I'm sure most of you are familiar with Perl's front door criteria. And the front door criteria allows for on-measure confounding of a treatment outcome relationship and adjusts for it by assuming that you've captured all mediators of the exposure outcome relationship. So you have this mediator variable, and that's the sort of the graphical picture of a front door. You're going through the front to adjust for measure confounding. And so this requirement of having adjusted for, having measured all the relevant intermediate variable is an important condition. And so what we were able to show is that, in fact, if you had proxies of the intermediate variables when you hadn't measured the actual intermediate variable, you can get a proximal version of the front door, which we call the hidden front door. And you can uncover that hidden front door using proxies. And then finally, recently, we've demonstrated how one could use proximal inference to combine experimental and observational studies. And so all of these papers are on the archive, and anyone interested can always, and their stages of being under review. I also wanted to mention that there are several other authors who have contributed to this area, and so we've been humbled by the level of interest and the speed with which this framework is being developed and adopted. And so maybe I can stop there and see if there are any questions. Maybe I just mentioned that this work is supported by NIH grants. And thank you so much for the invitation and for your attention.
Thanks a lot. Thanks for the talk. That was very interesting. I'm going to wait to see if there are some questions in the chat. But so I had a question which I'm not sure if I missed it or if it's a silly question. How robust is the whole framework with respect to the assumption? You know, like you have a DAG, that's kind of an assumption. How is it if it's not exactly independent conditional on what it should be, but roughly, I don't know, the mutual information is small or something like that?
Sorry, no, I think I understood what you said, but I didn't quite hear the question.
Oh yeah, so let's say so you start with the modeling assumption that you have your two
conditional independencies. Yeah.
How much
is the question what happens if it doesn't hold?
Yeah, what if instead of being actually independent conditional on that, it's, I don't know, the mutual information is small, or some, it's not quite independent, but like kind of. Is there like a...
Yeah, no, that's a fair question. To be, if the conditions do not hold, the extent to which you deviate from the conditions will be reflected in the lack of correction of bias. Like any identification formula. What's important here is I'm glad you asked this question. There are many settings where you get those conditions by design. So for instance, in time series data, so I do some work in air pollution where we're interested in the causal effect of air pollution on mortality. And we have time series data. And at each point in time, today I want to know what's the causal effect of the air pollution yesterday on mortality today among the elderly. And so in those settings, what you can do is your proxies, the valid proxy, you worry about confounding, and valid proxies are actually, you look at air pollution the following day, and that cannot causally affect the outcome. Because air pollution followed just by temporal ordering, causality flows forward. And likewise, mortality before your measurement of air pollution cannot be causally affected by your air pollution. So time is a good friend as a way of picking proxies. So we often pick baseline version of the outcome as an outcome proxy. And in some cases, like the one I described, if you have repeated measures, you can choose post-outcome measurements. The other point I want to make is that there is a literature on negative controls. And these are settings where there is knowledge about variables that cannot possibly scientifically known not to causally affect the outcome, and likewise outcome that cannot causally be affected by the exposure. And so those are in fact, negative controls are good proxies. But you're absolutely right that if those conditions, you have to be really careful. If those conditions cannot hold, you can end up amplifying your bias as opposed to correcting for it. And so those are really important.
Thanks. There is a question in the chat by Nicholas Irons about the intuition behind including the norm penalty on T in the objective.
Oh, so that's a good question. Oh, you can't see my screen anymore. The penalty is important, otherwise the risk can be made infinite, unbounded. So it's the usual reason to add a penalty is that's a regularization tool to ensure that the max doesn't blow up. And we've shown that it plays an important role in characterizing the asymptotic behavior of the estimator.
Great, thank you.
Okay. It doesn't look like there are any more questions.
All right.
So thank you so much.
Oh, thanks again for giving this talk. And so I'm going to stop the recording now. All right.